pull up our information here. Oh, my computer's dragging. Here we go. Okay. Now it's trying to do something. Is it going to do the blinky thing, or is it happy this week? Oh, it's doing the blinky thing. Well, let's see if it quits here. So go to the grade screen. Okay, changing screens made the blinky quit. I haven't done my assignment from last week. Okay, should have the 5.01 assignment done. I do not. I've just been going too many directions at one time. But this week we are doing logarithmic functions. And look, we have a quiz. Exponential and logarithmic functions mid-module check. And it'll be over exponential and logarithmic. So that's what we have this week is the log functions and the quiz. And then next week we'll look at graphing both types of functions and then test the week after that. So last week of January, we're testing. We're going to not spend a whole lot of time on this unit, but that's where we're at today is logarithmic functions. So let's switch over and take a look at that. We'll have some good notes to take for this log functions lesson. Okay, here we go. Logarithmic function. It says, suppose you were to graph the linear function. So let's do this. I'm going to put this Desmos up here, and we're gonna do what they're showing right here. But I'm gonna show it bigger on the screen. It's a lot easier to look at if we have Desmos loaded up than those little bitty graphs that they like to show in the lesson. Okay, so it said, suppose we had this graph 2x plus 3. Here's what that graph looks like. It's the red line right there. It crosses the y-intercept at 3, has a slope of 2. And we have learned in the past that we can find the inverse of an equation. And so the inverse of this equation would be y equals, let's see, x minus 3 divided by 2. Oh, I got to put x minus 3 in parentheses. X minus 3 divided by 2. That would be the inverse of this equation right here, the inverse. And we know it's an inverse because it reflects, oh, no, see, notice it says 3, 0, and that one had 0, 3. See, the inverse, the y's become the x's and the x's become the y's. They swap on an inverse of a function. So that is the inverse of a function, and it reflects over the line y equals x, the green line. So it's exact same distance away from that line for both equations, just opposite sides. They meet right there, and then they're the same the other direction. So this is an inverse equation, right? So we did that back when we were looking at linear equations and inverses and all that kind of stuff. But let's talk about this exponential equation. Get rid of that one. This is an exponential equation. Like we looked at last week, we were looking like 10 raised to the power of x. Remember, in an exponential equation, the x, or the variable, is the exponent. It's in the exponent. It's not down. So the x is the exponent. And a graph of an exponential equation looks something like that. Okay, so this one crosses at 0, 1. And we have this line of reflection, which kind of insinuates that we're going to be able to look at the inverse. What is the inverse? Gosh, your microphone's on, sir. The inverse of an equation is the logarithm, is the inverse of an exponential. Got some good music going there, Josh. See if I can mute you there. All right, I've muted Josh. The inverse would be the logarithm. Y equals the log of x. Look there, it crosses at 1, 0, where this one crosses 0, 1. It's an exact reflection over that y equals x line when we look at the graph of the log of x. So as opposed to 10 to the x power, we're looking at log base 10 of x. And those are inverses of one another. Kind of cool. So we're going to get into logarithms and learn more about how logarithms work and try to understand logarithms better. But I just wanted to show you how that is an inverse of the exponential equation. So they were showing the same thing with this little graph right here of that linear equation, and then talk about the graph of the logarithm and 10 to the x exponential equation. Same thing. I just showed it except on the big Desmos thing. So we're going to learn in this lesson, how are exponential functions related two logarithmic functions. We just learned their inverses. The base change property can help in what type of scenarios? And how can logarithms be used to solve exponential equations? So we learned about solving exponential equations last week. We're going to learn how to use logarithms in helping solve these type of equations. And we will be using our calculator this week a lot with logarithms. Let's go to page 2. All right, let me put this in our notes. Let's just start our notes right here. This is a great place to start. Last week, we looked at general exponential equations where you had y and you had some number as the base. That could be 2, 5, 10, 3, whatever number our base was. And x is in the exponent. We could rewrite this as an equivalent log equation as log base, the same base, whatever the base of the exponential equation would be the base of our logarithm. And our argument would go right here. Log base y would equal x. So this is equivalent. This is the exponential equation, and we can rewrite that as an equivalent log equation. So let's do an example. Let's say 100 equals 10 squared, right? 10 times 10 is 100, so we know 100 equals 10 squared. What's the equivalent logarithm? That's the same as saying the log base 10 of 100 equals 2. Log base 10 of 100 equals 2. 100 equals 10 squared. So what we see is whatever the base is of our exponential equation is going to be the base of our logarithm. Whatever the exponent is going to be on the other side of the equal sign from our log. And whatever the argument is out here becomes the argument of our logarithm right there. Now, I want to talk something about log base 10. Like on our calculator, you just see, we would say log 100 equals 2. This is the same thing. Because with logarithms, if we don't put a base, I didn't put a base there. This one I wrote a base. If we don't put a base, it's assumed to be 10 automatically because our number system is base 10. The number system we use is base 10, right? Every time you write a second, this is base 10, 100, 1000, the ones, the tens, the 100s, the places. This is a base 10 number system that you've used your whole life. So this is assumed to be base 10. Just like when we write this, if we do not write anything, that's assumed to be a square root. That's assumed to be a 2, right? This is an imaginary 2 right there. This is an imaginary 10 right there. There's certain things like that we don't write. Just like right here, if we write just x, there's an imaginary 1, right? We don't write the 1. We know it's x to the first power. We know this is the square root. We don't have to write the 2. With logarithms, we know this is base 10. We don't have to write the 10. So there's certain things that are just assumed unless you write something different. If we write a 3 here, we know that's the cube root of x. It's not just the square root. If we write a 3 here, we know that's x to the third power. It's not x to the first power. If we write a 3 here, we know that's log base 3. So understanding that if you do not see a number there, this is a 10. So these are all assumed. Write that, assumed. Highlight the assumed part. We assume this is a 1. We assume that's a 2. We assume that's a 10. Those are all assumed. Do not have to be written. Only have to be written if that's not true. Let me show you real quick on our calculator. I said that log base 10 of 100 equals 2. So with this calculator, it's different with different calculators. I'll show you that because Buzz has a built-in calculator that I like better than this one, but it doesn't show up until the assignment. If I want to take the log, here's the log button right down here in the corner. I have to put the number first. If I hit 100 and then log, the answer is 2. See, it says log 100 is 2, like I said, because 10 squared is 100. That's what you're looking at with a logarithm. What number do we need to take 10 to the power of to get 100? That's what this is saying. 10 to what power equals 100? That's what this logarithm is saying. Well, 2. 10 to the second power equals 100. So when I put log 100 in my calculator, it tells me the answer is 2. If I put 1,000, it's 3, because 10 times 10 times 10 is 1,000. That is the log. But with this calculator, I have to put the number in first before I hit log. Log 10 is 1. 10 to the first power is 10. So when we play with that, just realize I'm putting the number in first before log, because that's how this calculator. It's different with different calculators. So we'll look at others later on. So, but this is showing you right here how we can rewrite that logarithm. Y equals b to the x is the same thing as x equals log b to the y. So why is this important? From this simple logarithmic expression, we can rewrite the equation in an exponential form. So we can go back and forth. If we have a log that's easier to solve as an exponent, we'll write it as an exponent. If we have an exponent that's easier to solve as a logarithm, we'll write it as a logarithm. So we can go back and forth either way. Like, for example, well, that's a good one there. If we have log 2 of x equals 7, what's the answer? Like, I don't know. I'm not used to working with logarithms. Well, let's rewrite it. That's the same thing as 2 to the 7th power equals x. Because I rewrote it. The base is the base. Base 2, base 2. The number over here is the exponent. This is on the other side of the equal sign. That's the exponent. This is the argument. Well, 2 to the 7th equals x. Now that's easy to solve. I can just take 2 to the power of 7. Oh, the answer is 128. So this is log 2 128 equals 7. Got it. Easier to solve when I rewrite it as an exponent, because this I understand. 2 to the 7th power. Oh, that's 2 times 2 times 2 times 2 times 2 times 2 times 2. That's 128. So this is why we need to know how to rewrite those back and forth, because sometimes it's simpler to look at the exponential form rather than the log form. And I'll show you things that we can look at to solve it as a log, even with our calculator as well. In fact, let's get into that now. I know the lesson's going to get into a little bit. No, because this is with an x. We can't do this with x. We'll get this in a minute. Okay. So it rewrites it as 2 to the 7th equals x. So then you know, oh, okay, so that's log 2 of 128. Log 2 128, which is 7. Oh, let's talk about that real quick, too, because there's this other button on the calculator. Underneath the log, there's this LN button. That's a logarithm button also. Because we can write logs in any base we want to. You know, this is base 10. This is base 2. This is base 7. Right? We can write any base we want. Without using insulated again. Oh, wait a minute. What did you do, Mr. Brock? I wrote base 10, base 2, base 7, base 11, base E. E Yeah, E's a number in math. I don't know if that's been brought to your attention before. This is a number. This is not a variable. I'm not just using E like it's a variable. E is not a variable, it's a number. It's a number. Well, what number is it? Because I is a number in math, right? I is a number. It equals the square root of -1. We've talked about I. I is a number. Pi is a number. 1, 4, et cetera, et cetera, et cetera, et cetera, et cetera. Pi is a number. We have things in math that don't make sense sometimes. I is a number, pi is a number, E is a number. What is E equal to? Well, it's on your calculator. You ever see that little E button on your calculator? Because that's a number. And it equals 2.7182818284590. It goes on forever, kind of like pi does. It's very similar to pi in that respect. E is 2.71828, et cetera, et cetera, et cetera. E is a number. So we can have a log base E because you can have any number you want as the base. However, log base E of X is, we call this the natural log. E is called the natural number because in life, in science, when they study the world, they find E. There's this number that reoccurs in lots of calculations based on our current world and the surroundings that E plays into. This 2.71828. They've discovered that somehow this relates to a lot of things that we do. So this is called the natural number. So this is called the natural log. So if you have log base E, they just write it like this. Natural log. That's the natural log. It's the same as this, but we don't write it this way. We write it this way. And it has a button on the calculator for the natural log. So if we take the natural log of E, it equals 1 because that's E to what power equals E? E to the first power. The natural log is base E. So just understand that. Just accept that. We'll work with it a little bit, but just know that when you see that, that's a logarithm. Ln is a logarithm. It's just base E instead of base 10, instead of base 3, instead of base anything. It's base E, which is a number in algebra, in math, in life. E is a number. So bring that up there because they talk about it a little bit right here. A logarithm with base E, which equals 2.71828, is known as the natural log and is written as Ln of X. So y equals the natural log of X. So when we see Ln, we call it natural log. So natural logarithm, it's a log with base E. Okay, so it says evaluate the logarithm expression log 2 of 128. This expression isn't set equal to a number, so we'll set it equal to X because it just says log 2 of 128. What? That's a number. Log 2 of 128 is a number. Doesn't look like a number. We're not used to thinking of it as a number, but that is a number. So if we set it equal to X, next thing we would do is let's rewrite that. So that really means y equals 2 to the X power. So 128 equals 2 to the X power because we had log 2 of 128. That's what y is. So that's the same as X equals log 2 of 128. It's 128 equals 2 to what power? Well, when we calculate 128, that's 2 to the 7th power. So we know X equals 7. And then we can substitute this back into the original equation. 128 equals 2 to the 7th. That means 7 equals log 2 of 128. The solution is confirmed. 2 to the 7th is equal to 128. So, terminology. Let's look at the terminology here. Put this in our notes. log 3 of 9 equals 2. Okay, this is equivalent to 3 squared equals 9. So this is called the base, just like this is called the base. All right, that's the base of our exponent. This is the base of our logarithm. This is called the argument, just like this is called the argument. And this is called our exponent.
Oh, you mean in between? Those are bonds. I see what you're looking at now.
The same as that is called our exponent.
Okay. Yeah.
So just getting our terminology straight, just so we understand when we use the word the base, our base needs to be the same, or our base is 7. We understand which number we're talking about, right? When we talk about the argument would be this number here that follows the base before the equal sign. The argument in an exponential is what it equals. So just understand which number is which, and base is a big one that we talk about very frequently. Same thing. The base is the base when we rewrite it. So we're going to have that in our notes, just so we understand the correct terminology. Logarithms are base, argument, exponent. Exponents are base, exponent, argument. Same thing. All right, let's create log functions, which is very similar to how we did when we created the exponential function. Remember, with an exponential function, we had the x said 1, 2, 3, 4, and then the y over here was 2, 4, 8, 16. Well, with a logarithm, it's exact opposite. Remember, because since it's an inverse, the x becomes the y and the y becomes the x. It kind of goes back and forth. So the y, or the f of x is the same as y. 1, 2, 3, 4. That's what we saw in the x with exponentials. 1, 2, 3, 4. And the x is 2, 4, 8, 16. Now notice how it increases. The y goes 1 plus 1 plus 1. But this is plus 2 plus 4 plus 8, which means this is not linear, doesn't graph a line. But when we look at it a different way, just like with exponentials, this is actually times 2 times 2 times 2, where the y is 1, 2, 3, 4. So since the x is going times 2, we know this is the graph or the table for log base 2 of x. And we can check that to see log base 2 of x. So if x is 1, if x is 1, x is 2, I'm sorry, x is 2, 2 to what power equals 2? Well, that'd be the first power. That's why it equals 1. Put it down here. 2 to what power equals 2? 1. If x is 4, we got log 2 of 4. So 2 raised to what power equals 4? The answer is 2. If the x is 8, we've got log base 2 of 8. 2 to what power equals 8? Third power. 2 times 2 times 2. When x is 16, that's 2 raised to what power equals 16? That's 2 to the fourth power. 2 times 2 times 2 times 2. 4 2's multiplied together, you get 316. So it does check out. Based on the data, this is log 2 of x. All right, evaluate the natural logarithm. So how to solve natural log of x equals 3 and round the solution to the nearest 100. So we'll look at this video.
To solve the natural log of x equals 3, first rewrite the natural logarithm in exponential form. Remember, the natural logarithm represents a logarithm with base e. The next step is to solve for the variable. Using your calculator, find the value of e cubed. The final step is to check your work. Substitute 20.09 into the original equation to verify the solution. Using your calculator, find the value of the natural logarithm 20.09. The solution has been verified.
Okay, I want to point out when you're verifying your solution, they rounded this number. When they took e to the third power, they rounded it to 20.09. Because if we look at it in the calculator, e taken to the third power is 20.08553692. They rounded it to 20.09. So when they said, let's double check our solution, and they put in 20.09 and took the natural log of that, 20.09. When I take the natural log of that, it doesn't equal 3. It equals 3.000222148, et cetera, et cetera, et cetera, because it was rounded. So since it's rounded, it's probably not going to equal exactly 3. But it's going to be close. It's going to be close enough to know that it's like, okay, yes, that's just a rounding error issue right there. That's why it's not exactly 3. So that is correct. 20.09, if it's rounded to the nearest hundredth, is okay. So just be aware of that when you're using numbers like that in your calculator, with dealing with E especially, because you'll end up having to round it. All right, let me go back to sharing it like it was before I forget. All right. All right, this wants us to solve log B 32 equals 5. This is good to practice. Log B 32 equals 5. All right, if you got paper there and pencil, taking notes, write this one down. Log B 32 equals 5. And I want you to rewrite that as an exponent. I'll go back down to where I showed how to do that at the top of the screen. Rewrite that as an exponent and see if you can solve this. What is B? I'll give you a minute to work on that. I'm going to open up the chat where I can see what anyone types. But what is B? B equals what? So I'll put that in the chat. See if we can solve this while we have a relatively simple problem to work before they start getting more complicated on it, because you know they're going to get more complicated on us. Log B of 32 equals 5. What is B? But make sure you can do this now in class before we turn you loose to have to do the assignment by yourself.
And then it's not your own line.
All right, anyone got an answer yet?
I know, you're like, but I want
Even if it's a
this.
guess. So we're going to look at it as a class here in just a moment. Bridget's got an answer.
Have an answer on there.
Anybody else? Allison agrees. Everyone else still working on that?
Let's look at it.
Okay, not a problem. All right, for those of you who are still working on this, I'll start on mine. So this is the same as
And this one is
rewriting this. I rewrite this as an exponent. So 32 is the argument. So 32 equals, the base is the base. The base of this is the base of this. And my exponent. So there's the first step. Good job, guys. 32 equals what number taken to the fifth power? Well, technically, the way you solve that is you take the fifth root, right? The fifth root. But if you know what number you multiply it by, it's got to be a very small number if you're multiplying it times 5 times. But the fifth root of 32. My calculator will actually do that because it has square root right there. But if I shift, it's got, third root and y root. I can choose what root. So 32, it wants to know what root I want. I want the fifth root. And the fifth root of 32 is 2. Yeah, because b equals 2. Because 2 times 2 times 2 times 2 times 2 equals 32. So that is 2 to the 5th. So log base 2 of 32 equals 5. Log base 2 of 32 equals 5. So b does equal 2. That is the base. So good job for those of you who got that. You're still working on it. What I have to do is figure out what number to the 5th power is 32. Hopefully you at least got that written correctly. It says rewrite in exponential form. What is the base of the equation? Well, it was b because we were trying to figure it out. And it says what power will it be raised to? The 5th. And what will it be equal to? 32. All right, and then solve for the variable. How you find the value? You take the 5th root, technically. 5th root of each will get b equals 2. And then you can check your work by putting it back in there. Log 2 of 32 equals 5, which means 2 to the 5th equals 32. And 2 to the 5th is 32. So it does equal out. Let's look at page 3.
Yeah.
Okay. This is great. Not all logarithms are base 10, base 2, base e. It's going to be helpful to know how to change the bases so your calculator can use it. Yes. Let's play with this on our paper. We can go through the buzz lesson, but this is something we can play with on our paper and get this. So let's say we have some problems like log 2 of 8 equals x, or log 4 of 64 equals x, or log, let's do something kind of odd. How about log of 13? Well, what number do I want to put there? I want to put some weird number. Oh yeah, there's 2. So log 13 of 371,293 equals what? And we're like, oh my gosh, Mr. Brock, this is ludicrous. This is crazy. Well, let me tell you, there is a simple way to solve all of these with a calculator. And you're like, wait a minute, you showed us the calculator. It's log base 10. That's log base 10. None of these are log base 10. I can't just punch these number in. If I do 371,293 and hit the log button, it says 5.5697 because that's log base 10. 10 to the power of 5.569 is 371,293. Some calculators, and I'm not going to use this, some calculators like this one allow me to shift and choose what base. I can choose what base I want. But we're going to assume that our calculator cannot do that. And I'm going to show you how you can put this into any calculator, even a simple calculator that only does base 10, and solve this problem. So if we have log base b of y, that is the same as log of y divided by log of b. Wait a minute, what base did you use, Mr. Brock? Because you didn't write a base. Oh, those are base 10. Notice there's nothing written there. I put no base here, so these are base 10. Hey, the calculator's base 10. So I can just punch this in my calculator as log base y over log base 10. So if I want to solve this, I can take log base 10 of 8 and divide it by log base 10 of 2. If I wanted this one, I can take log of 64 and divide it by the log of 4. And that gives me this one. I can take the log of 3,771,293 and divide it by the log of 13. And these I can do all in my calculator because these are all base 10. I wrote them as base 10. So let's do that. Let's just punch these in the calculator and see what it comes up with. So log 8 divided by log 2. Log 8 divided by log 2 is 3. That one we probably could have done in our head because log 2 8x means 2 to the x equals 8, right? Right, that's the same thing. 2 to the x equals 8. 2 to what power equals 8? So we knew the answer was going to be 3. 2 to the third power is 8. But this is how we can do it without converting it to an exponent. We left it as a logarithm and found the answer. How about log 64 4?
Mr. Brock,
Yeah.
so if the base is anything other than 10, you use this?
Yep.
Okay.
You can do it. See, because it didn't matter. I just put B over here, generic, any base. So this is base 2, this base 4, this base 13, and I converted them all to base 10 by doing this. So if I do log 64 and divide it by log base 4, the answer is 3. So this answer is 3. How about this nice log 371,293 of 13? What does this equal? 371,293, the log of that divided by the log of 13. That's just 5.
In the water guys, what are the big orange with the big red ball?
That basically is 13 to the 5th power equals 371,293. That's the same thing.
Here, can I see your document?
So what's great about this change of base formula is I can change it to any base I want to.
Daniel,
I could say log base 3 of 8 divided by log base 3 of 2. This is the same as this. I use base 3 instead of base 10. I could say log base 19 of 8 divided by log base 19 of 2. And the answer is still going to be 3. This change of base means I can change it to any base. I just changed it to 10 because that's what my calculator uses. But I didn't have to. I could have said log E of 8 over log E of 2, which means it would be ln 8 divided by ln 2. And the answer would still be 3. So I could have done the same thing using the natural log. Instead of base 10, I could have said 8 natural log divided by 2 natural log. It still equals 3. So my point is the change of base formula means we can change this to any base we want to. But generally, we would always want to change it to base 10 so our calculator can do it. But we don't have to. We could have made them base 19. Let's see. Let's use that fancy feature on my calculator here. Got the shift where I can choose what base I want right there. So if I said 8, what base? I want base 19. So there's what 8 base 19 of 8 is. And then I'm going to do divide it by base 19 of 2. 2 base 19. See, the answer is still 3. It didn't matter. I made it base 19 and the answer is still 3. So this is the change of base.
Is more energy released, new bonds are formed.
Change of base.
These two highlighted ones, answer this up here.
Change of base. Now, I'm gonna stop presenting for a moment because I'm talking about there is a problem, and I think it's in this week's assignment. There is a problem in this week's assignment that says, here's this problem. Tell how to use the change of base to solve it. And every year I have to count that wrong for tons of people that convert it to an exponent and solve it that way. It's like, I know you could convert it to an exponent, but that's not what the question said to do. It said use the change of base to solve it. And since the question says describe how to use the change of base to solve it, you don't convert it to an exponent. The answer is wrong if you're telling me how to convert it to an exponent and solve it.
Okay, and then answer.
Pay attention to what the question's asking. It says, describe how to use the change of base formula to solve this, and then round your answer to the nearest thousandth or whatever. If it tells you to round your answer, that means you should go ahead and solve it. Don't just tell how to solve it. It says, describe how to use the change of base to solve it, and round your answer to, which means show how to do it. Tell how to do it, show how to do it. Same thing. So I'm good with that. You can just work it using the change of base formula and don't really have to use other words. In math, that's explaining. I'm happy with that. So here is in our lesson, as it comes back up, in our lesson on page 3 is the change of base formula right there in the middle of the screen. Oh, it's going to give me the blinky. Hopefully it'll quit. Change of base, log b of y would take log y divided by log of b, base 10, or whatever base you want, but calculator is base 10. You can also use the natural log. There's the log 8 divided by log 2. You could do it with natural log. What is the natural log of 9? Oh, round or answer to 3 decimals. So this wants to know if we just know how to do this, because you have to use your calculator on these things, because nobody knows the natural log of 9, because 2 point all that raised to whatever power equals 9. Hit 9 natural log. There's the answer. 3 decimals. 2.197. Submit. Great job. See, that's nothing we would know in our head. We can't solve that in our head. We got to have a calculator to solve. E to what power equals 9? Well, e to the 2.197 power equals 9. So this is just making sure you know how to use your calculator. There it is, 2.197.
Andy, can I see your document, please?
Let's see, change of base. Evaluate log 7 of 15. All right, if you have a calculator there, see if you can get that before we get to the answer on the screen. Log 7 of 15. 7 raised to what power is 15? Oh, well, that's going to be a decimal because 7 squared is 49, and this is smaller than 7 squared. So it's 1 point something. So if you have a calculator on your phone, you can do this because your phone will have a logarithm. If you turn it, you may have to turn it sideways, but it'll have a logarithm. Log 7 of 15. You may have a calculator on your Chromebook you can pull up. What is the answer to log 7 of 15? Use the change of base. Right? Use the change of base to find log 7 of 15. So let's go through the steps where you're seeing if you can get ahead of it. See if you can figure that out. So according to the change of base formula, you can divide the common log of the argument by the common log of the base, which means base 10. Common log means base 10. When you see the words common log, that's base 10. In fact, I'm going to put that in our notes. Let me put that in our notes. Where's my notes? There's my notes. If you see the words common log,
Don't guess, go look at your gizmo.
means base 10. I don't like that G. Means log base 10. Common log means base 10 because that's the common what we use. We use base 10 numbers in our society. So that's what common log means. It means base 10. So when you see that, go ahead and change the base formula. You can divide the common log by the common log. So in your calculator, hopefully you've done this. Log 7 of 15, log base 7, would be log 15 divided by log 7. Log 15 divided by log 7. There's the answer I got. Hopefully you got something similar to the nearest hundredth. So that'd be 2 decimals. Our answer should be 1.39 rounded to the nearest hundredth. Is that what you got? We can divide that. It's about 1.176 divided by 0.845, 1.39 rounded to the nearest hundredth. Dividing log 15 by log 7. Okay, let's look at example 2. Evaluate natural log of 4. That you just, they did with change of base. They said natural log of 4 divided by natural log of e. That's interesting. We could do 4 log divided by e log, because that's the base. But however you do it, it should be 1.39 if you round it to 2 decimals, because the 8's going to round up. Or you can just punch in natural log of 9. If you should have the natural log button. Oh, I'm sorry, natural log of 4, not 9. Natural log. You should have a natural log button. 1 point, same number. 1.39. All right, let's look at page 4. Get a little bit more into the solving of logarithms. Uses of logarithms with different bases. Okay, this is a good sample program. Example problem we're gonna work. When you turn 16, and we looked at this in the last lesson. We looked at it in a different way though. We looked at something similar. We looked at something similar when we're talking about money and stuff with exponentials. When you turn 16, grandma gives you $50. Hey, I got $50 from grandma. Thank you, grandma. I'm going to put that in a savings account, and I need $2,500 so I can have a down payment on a better car, a nice car, right? New car. This bank account pays me 3%, and it's compounded monthly. How long is it going to take me to have $2,500? Right? We looked at a problem last lesson, like you started with this much money, you got this much interest, and in this much time, how much does it grow to in 5 years, right? We did something like that. This time, we don't have the years. It just wants to know how long is it going to take me to get $2,500. And I'm going to have enough by the time I turn 18 because that's what I want to buy the car. So let's write this down. We got $50. The bank pays 3%. How often did it say? Monthly. And how long? Oh, I'm writing that terribly too. I'll show you. Okay. So start with $50. I get paid 3% monthly. How long to have $2,500? Because that's what I want. And we use the amount equals principal times 1 plus R over N to the NP that we had last week. All right, that's our interest formula. And if we plug in what we know, the amount we want, see, we don't know time. We want to know how long is this going to take for this $50 to turn into $2,500. I'm not putting any more money in there. That's all the money I got. So $2,500. If I start with 50, let's figure out what's in parentheses here. 1 plus R. 1 plus 0.03 divided by 12. All right, that's what that is. 3% as a decimal. Monthly, so 12 times a year. Let's get a number to put that as. 1 plus, and I'm going to put 0.03 divided by 12. So that's 1.0025 and 12p. So there's our problem. And we need to find out how much time it's going to take us to get $2,500. Can we solve that? That looks pretty complicated, Mr. Brock, because we've got the variable up here in the exponent. I can do some of this. Like I can simplify, divide both sides by 50. 2,500 divided by 50 is 50. So 50 times 50 is 2,500 equals 1.0025 to the 12t, but that's about as far as I can get. Solve it in exponential. That's about as far as I get. I don't know where to go from there. I don't know if I'm going to have the money by my 18th birthday or not. Well, let's see. Go back here to the lesson. What do the variables represent? A is the amount of money in the account after so many years. P is the principal, what we started with. R is the interest rate. N is the number of times that you get interest each year. So when we substitute, we get down to, here's what we had, 50 equals 1.025 to the 12t. But the only way we know to solve exponents, remember, is we have to get them at the same base. We have to get the same base. If we had 3 to the x equals 9, if we can write them as the same base, 3 to the x equals 3 squared, same base, we know x equals 2. So this is 50 to the first power. This is 1.025 to the 12t. I just need these as the same base. Oh, I have no idea how to write 50 and 1.0025 as the same base. No idea whatsoever, right? And that's what we learned how to do last week. Don't know how to get those as the same base. See, it's 50 that, but 50 and 1.025 do not share a common base. So we're going to learn how to do this, though, right here at the bottom of the page. We're actually going to do this in just a minute. But let's look at a different problem first. So we'll come back to this. I'm gonna go over here on the side and write this one down. 4 equals 7x plus 1. Okay. And we're going to go through their steps there. Okay. So we can rewrite this. If we got this is the same type of problem, right? Over here, we've got a really odd two numbers that we cannot make the same base. We can't make these the same base either. 4 and 7, I don't know how to make those the same base. I can't do that. But I can rewrite this as base 7c. So this is log base 7 of 4 equals x plus 1. I can do that. Rewrite this as a log. The base is the base. The argument is the argument. The exponent is the exponent. So I can rewrite that. So that's the first step. Since I can't solve it by getting the same base, let me change it to a logarithm. And I can calculate this because this is log 4 divided by log 7 equals x plus 1. And then if I subtract 1 from both sides, so whatever number log 4 divided by log 7 is, I can subtract 1, and that's what x will equal. Because it's x plus 1, I subtract 1 from both sides. So let's find out what that equals then. We can take our calculator and figure out what log base 7 of 4 is, because we can do log 4 divided by log 7. It's that weird number. And subtract 1 from it. So negative 0.28. Let's go 3 decimals. That would round up to 8. Because it's 7.5, so it rounds up. So x equals negative 0.288. Let's check it. Let's go back up here and say, all right, does it equal, there, so 4 equals 7 to the negative 0.288 plus 1 power. So let's see. If we take 0.288 negative and add 1, that means 7 to the power of 712 will equal 4. Let's see if that works. 7 raised to the power of 0.712. 3.996. See, that does equal 4 because I rounded it. If I wouldn't have rounded it and used the whole thing, which goes on forever, it'd be exactly 4. But I rounded it to 3 decimals. When I took log 4, divided by log 7, subtract 1, and round to 3 decimals. And so that checks out. So wait a minute. So that gives us a strategy to figure out how many years it's going to take our $50 to turn into $2,500. Let's rewrite this as a log. So this is base here. So log base 1.0025 of 50 equals 12t. Now we're on to something. I put 15 and said 50.
All right, now for
Brain's still not working well today. 50. So that means over here, I can take log of 50 and divide it by log of 1.0025, and that will equal 12t. So whatever I get for this answer, I just got to divide it by 12. All right, so whatever log 50 divided by log 1.0025, whatever number that is divided by 12 will equal how many years? I really hope we get this money by our 18th birthday so we can buy that car, right? Because we did this at our 16th birthday. So let's see what that's going to equal. Log 50 divided by log 1.0025 equals divided by 12. We'll have $2,500 in just 130 years. 0.56. So if we take that 25 or that $50 that grandma gave us for our 16th birthday and put it in this bank account, 3% monthly, 3% a year, monthly interest, by the time we're 146, we'll have enough for that down payment for a car. I think we're going to run a little short of our timeline to have this by our 18th birthday. Takes 130 years. You see how we did that, though? I want to go back up to this. We had 50 equals 1.0025 to the 12t. So we rewrote it as a logarithm with a weird base. Look at what base we used. That's the base of our logarithm because that was the base of our exponent. But with our change of base formula, we just take the log 50, which is there, it goes on top, and we divide it by that weird number with the common log. Again, these are both log 10 now, base 10. And then we divide by 12 to get t. So whatever that equaled, we divide it by 12. We got 130 years. That's right here. We get down to that 50 equals 1.0025 to the 12t. So you rewrite it as a logarithm with that weird base equals 12t. They went ahead and put numbers in there. Log 50 is 1.6989700. Log 1.0025 is 0.0010 over that. They divide it, and then they divide both sides by 12 to get 130 and a half years. So we can use logarithms to solve exponential equations that we cannot make the same base. Solve e to the 2x equals 30. Well, let's look at that one. Okay, here's one that we can't get these to the same base. I don't know how to write 30 in base e. So we should rewrite this as a logarithm. That's all. So log base e would be ln of 30 equals 2x. That's log base e. So if we divide by 2, whatever the log base natural log of 30 divided by 2 is going to equal x. So x will equal, hello calculator, natural log of 30 divided by 2, 1.7. And 0, 0, so 1.70. I guess we can go another decimal. Let's see what we got. We call that the natural log. So you rewrite it as natural log 30 equals 2x. And we get to 1.70 when we divide by 2. All right, that's not too terribly hard. It's just you gotta make sure step by step you're not doing something wrong, right? A, P, 1 plus R, and T. Let's just go back and make sure you know what that is. Rate of change. T is the time the growth occurred. So they play around with some of these and they just change the letters to mean the same thing. Like here's an example of a lizard population. And instead of like A, they're using L of T, lizards over time. They change the variables. And so they say, all right, if we use this exponential equation where we start with 14 lizards and it doubles every year, how many years, find the population each. Oh, they want to do a change of time increments. Okay. That's what we're looking at on this. Okay, let me get another sheet of paper for time change here. Here's another thing they want us to be able to do. If we have these lizards over time, that they start with 14 lizards and they double every year, and they say we want to be able to find every month. Okay. Change in time increments. Change increments. Change increments. So this is in years, and they want to know months. So this is years. And they want to know months. So to do months, we would change this to 14. Instead of 2, we're going to divide it by 12. And this is going to become 12t because we're changing it to 1/12 to the 12th power. See, what we're doing is we're multiplying that by 1/12, and we're taking that to the 12th power. We're substituting that in here. We're multiplying that. Well, 1/12 to the 12th power. Well, that equals 1. So we're not changing the equation. We're just rewriting it in a different way. Let's put that in our calculator just to prove to ourselves. Parentheses 1 divided by 12. And if we raise that, click here, to the 12th power, 1/12 to the 12th power. Oh, wait, that's something really weird here. 1.12 to the -1. That is not right. What did they do here? Yeah, 1/12 to the 12. Oh, 2 to the 1/12 to the 12th power. That's what I was doing. I left off the 2. This is 2 to the 1/12 to the 12th power. Because we're changing this 2 to the 1/12. Right? That's what I did wrong. I wrote that wrong. Two to the 1/12th power. That's what I'm doing. 2 to the 1/12th. I'm sorry. 2 to the 1/12th to the 12th power. If we remember, do I have that handy? Somewhere I've got that here. When we're talking about exponents, we also talked about power to a power. If we take a power to a power, x raised to the m raised to the b, you multiply those together. Like x to the third to the fourth power is x to the 3 times 4, or x to the 12th. So if over here, if we're changing this to 2 to the 1/12 to the 12th power, 1/12 times 12 is just 1. So this is 2 to the first power. So by substituting 2 to the 1/12 to the 12th, and then raising that to the power of t makes that 12t because you multiply those together. This is still the same as this because we know that 1/12 to the 12th power is still just 2 to the first power. That doesn't change anything. So 2 to the 1/12. If we look back over here, 2 to the 1/12 is 1.059. We'll write that in our notes there. So 2 to the 1/12th power is the 12th root of 2. And we can actually put that up on here. Figure out what. 2 raised to the power of parentheses 1 divided by 12 is 1.059. So this right up here will give you every year. This right here, L of t, is monthly. We want to know every month how many lizards we have. We can use this equation. This is monthly, 1.059. Instead of doubling, every month we're getting 1.059 more lizards. So changing your time increment. So 14 times 1.059, 12t is simplified. Now t is still in years, but the base has changed. What does that tell us? Tells us the growth rate, right? 5.9% per month. Doubles per year. Doubles every year, but 5.9% per month. That's what we did. We changed the increments from how much does it change per month compared to how much does it change in a year. Well, it doubles in a year. It told us at the start. So what is that per month? Well, since this is larger than 1, this is growth, and it's 5.9%. 0.59 as a percent. So that's what it wants us to do. Same thing. The value of a sailboat decreases 12% per year. Here's the formula: 50,000 times 0.88 to the t. So that means you have 88% left because you lost 12%. Find the rate of decay per week. So you're going to take 0.88 to the 152nd power and make it 52t. The 152nd power and 52 on the outside. Then you're going to put that in the calculator to figure out what the 52nd power of 88 is, which is now you're losing 0.2% per week because it's 0.998. 0.998 is less than 1%. 0.2%. Okay, here's our lesson summary. Then we're going to look at some sample problems, 1 or 2 before we run out of time here. There's our essential questions. Here's the steps to solve a log equation. Rewrite it. Rewrite the exponential equation as a log. Solve for the variable. Check your work. A log function is the inverse of an exponential function. And we know how to write those back and forth, right? Right here, y equals b to the x is the same as x equals log b to the y. Here's the change of base formula, which is important, so we can use our calculator. If we have unequal bases, we can write them as a log and then use the change of base to put it in the calculator. And here's how to do that. Change different time intervals, 1 over c, and then put c to the t outside. So if you start out with this, whatever the time interval you're changing it to. If it was years, you want to go to months, you make that 1/12 and 12t. If you want it to be quarterly, it's 1/4 and 4t. Depending. Daily, 1/365 and 365t. Changing time intervals. But let's look at a sample problem or two before we run out of time. And do some practice. Okay, we're going to skip this. This is one of the easy ones. What to the third power is 1,000? Well, we know that's 10 to the third power. So let's skip some of the simple ones. Get something a little more complicated. Oh, here's a pretty good one. Log x equals 1. What's the answer? All right, I'm going to write that down on my paper. You work that and put the answer in the chat. Rewrite that as a logarithm. As an exponent. It's already a logarithm. And figure out what the answer is. If I rewrite it, what is the answer? Log x equals 1. What is x? If you rewrite that properly as an exponent, it gets real clear. You'll go, oh, that's it. I got it. Got 4 choices on the screen. What's it equal? 0, 1, 10, or 100? Becca's got a number out there that she's a little bit confident on. This is good practice to make sure you know how to properly rewrite it as an exponent. Write it as an exponent. Here's what I get. Log x of 1. It's base 10 because it didn't give us a base. So it's 10 to the first power equals x. What's 10 to the first power? Yeah, x equals 10. Base 10, they didn't put anything, so we know the base is 10. 10 to the first power. Yeah, good job, Becca. You're on top of that. 10 to the first power. Natural log of x equals 2. What is x on that? I can guess. I haven't put it in the calculator yet, but I can guess. Let me rewrite that one. Then I just have to put it in my calculator to solve. Pretty sure I know what it is without putting it in the calculator, but it's all about writing it properly. I'm gonna show you what I rewrote it as, and we'll see if you get the same thing. Natural log of x equals 2. So that means e squared equals x, because this is base e. E to the second power equals whatever the x is. So e squared, that should be 7.39, but we'll put it in our calculator. Oh, that's wrong. Wrong button. E squared. So e squared. 7.38. Yep. 389. So it rounds to a 9. Or you can say e times e. Same thing. Fabulous. Log base 4 of 8. That's just a simple calculator problem. Log 4 of 8. That means you take the log of 8, divide it by the log of 4, and it's 1.5. Simple calculator problem there. Let's look at page 7. See if there's something more complicated over here we need to practice. Solve each of these exponential functions. 5 to the x equals 20. Let's do this one, and then we'll go look at our assignment. 5 raised to the power of x equals 20. We know how to solve exponentials. You just get them to the same base and then drop the base. The problem is this is 5 raised to the base of x. Bigger on the screen. 5 raised to the base of x. I don't know how to make 20 a power of 5. If it's 25, this would be easy, right? X would be 2, but it's not. Not 25, it's 20. So we need to rewrite this as a logarithm and use the change of base. All right, how you doing on that? Do you have a rewritten?
Yeah.
5x equals 20 would rewrite as log, the base is the base. That's the base. This is the base. Log 5. 20 goes over here. Exponent goes there. So log 5, 20 equals x, which means it's just log 20 divided by log 5. Which equals what? Let's see. 25, 1.861. We'll see how many decimals they wanted at. Oh, let's see. 1.8. They went 2 decimals. 1.86. All right, I do want to show you the assignment and the calculator that Buzz provides because it works a little differently than mine. Let's go look at the assignment. Start. Which log function represents the data in this table? That's what it starts at. And it starts out with 3, 4, 5. So you may have to go backwards to get 1 and 2, or just figure it out from here. What's happening each time? How many times is that being multiplied? So is this log x5, 6 times log x, log 6x, or log base 6 of x? Solve log of x equals 4. Log of x equals 4. This is base 10, obviously, because there's no base listed. Evaluate natural log of 7. All right, let me show you the calculator that Buzz has built in. There's a calculator up here in the menu. If you haven't looked at it before, haven't tried that. If that's ever missing, email me. It means I forgot to add the calculator because that's an option. I can put the calculator or leave the calculator off. And I try to always make sure you have the calculator. But if I want to do log and natural log, they're right here on the middle row on the left end. Natural log and log. If I want to find the natural log of 7, my calculator that I was using on my computer, I had to put the 7 in first. But if I do that, look, it says no. What natural log you want? I think I'm doing 7 times the natural log. On this calculator, let's see. Clear. Oh, clear everything right there. Clear. Close that. I hit natural log first on this calculator because then you see there's a parenthesis that says, what number do you want the natural log of? I said 7. See, it shows it. Natural log of 7 equals this. Hey, I got that one done. 1.9459. So on this calculator, you hit the log button first and then tell it what you want the log of. I want the log of 100. Well, that's 2. So hit the log button first, and then what number do you want the log of? Okay. Just wanted to show you that. 5 problems. You have 5 problems. So, all right, everybody, we're about out of time. We will be meeting Thursday and Friday, so I'll have some fun things. You can bring any problems you're having there. Hey, I don't understand this problem. I'm not doing well. Bring them to class. We can work them as a class. I'll also try to have some stuff to do outside of our lesson because it's not going to take us 2 days, even or 5 problems. So, all right, guys, have a great couple of days. I got to get on a bus here shortly and head south. But we will see you guys on Thursday.